we are going to study the special relativities. Special relativities has two fundamental statements. First one is the relativity principles. This means laws of physics are the same for all inertial observers. The same equation for electromagnetism holds independent of a frame we use. Speed of light is obtained from the fundamental equation of the electromagnetism, Maxwell's equations. So this suggests the constancy of the speed of light. So also Galileo Galilei considered the relativity principles. So in his relativities, we call the Galilean relativities. F equal ma. This is a fundamental equation for the mechanics, holds independent of a frame we use. But Galilean relativities unfortunately fails in electromagnetism. Many scientists applied Galilean relativity to find the mistake in the electromagnetism, and nobody succeeded to find the failures in the electromagnetism. Then Einstein considered electromagnetism have to be the right, correct ones. Then we need to modify the mechanics, Newton's mechanics. This is the first fundamental statement of the special relativities. The next one is the constancy of the speed of light. Speed of light is 3 times 10 to 10th centimeter per second, and it is the same for all inertial observers, independent of their velocity to the source of the light. So this situation, the source of the light doesn't move, and light emitted from the source of the light and traveling to the light with the speed of the c. So second statement said this light observed by the two persons. One person doesn't move with respect to the source of the light. The other person is moving with respect to the source of the light. But both people observe the speed of the light is a c. This is the meaning of the constancy of the speed of the light. Let's review the Galilean coordinate transformation. We consider the two frames. X prime, Y prime frame is moving to the right with respect to the XY frames. Relative speed is expressed as u. So actually this is, we have x and the x primes. Then at the time of the t equal t, the origin is moving to the right. This length is expressed as ut. So for the x prime frames, this length is x prime. And if you observe that this length is x, so x have to be equal to the x prime plus ut. Very natural to believe. And in the case of the y, this length should be the y is also y primes. Y and y primes. And the g also say g and g primes. And we expect the time is the same for all the people in the world. So we use these four equations. Then find the derivative of x. We use this first equation with respect to times. Then it becomes dx dt equal dx prime over dt plus u. So this is speed on the x frames plus u. If you consider this is c, the speed of light, c, and this is c, plus u, it doesn't happen. So actually we need to modify the Galilean coordinate transformation when we consider special relativity. But most of in our daily life, we can safely use this equation to calculate relative velocities. Actually, this equation is valid approximately when the speed is much slower than the speed of light. Then I'd like to review the Galilean relativities. So if we don't consider the object whose speed is comparable to the speed of light, so object is moving much slower than the speed of light, then we can safely use this equation. Then find one more derivative. It becomes here, because the u is constant. Derivative of the constant quantity is 0. So from this equation, the acceleration is the same. So F equal ma is a Newton's second law, holds independent of the frames. But this is what we call the Galilean relativities.